All right, guys, so today, like I mentioned before, and we've been waiting on this one for a while now, we're actually going to start to apply this on a three-dimensional form, right? So it's no longer just in the z direction. Now we need to really focus on vector control a little bit more acutely than we've done so already. So first things first, we need to make a surface to apply this to, and then we're going to apply it to that surface and realize that it's all wrong. So, oh yeah, it's going to be way wrong.
Are you recording?
I am. Thank you for reminding me. So I'm going to probably build this in like the front view. It'll be very similar to the one we did before, I think. Actually, you know what? No, I'm going to do it on the top view. And I'm going to do a simpler curve than I did before, where it's just kind of something like that. Then I'm going to copy that upwards, and then I'll just flip it around 180 degrees, kind of like that, okay? So we're making like a saddle surface.
Do we need to do this?
Yeah, I'll give you a second to create a surface for it, but so I just created a surface kind of like this. It's just a warped surface. You guys don't have to do exactly the same curve as me. You want me to make it simpler? All right, here. No, all right. This actually probably is better for you guys to visualize anyway. So I'm just going to do a curved surface like that. Not warped, just curved. Okay. So you can just pull your curved surface thingy straight up. All right. So while you guys are going to do that, I'm going to start to explain the first difficulty we're going to have, right? We built our definition, we built this whole thing off of a rectangular grid. The rectangular grid is not a surface-dependent application, right? And if you recall, there was another method of subdivision that we used in order to break apart a three-dimensional surface, right? Do you guys recall what that was? No.
What did you say?
What we used in order to break this down and subdivide it.
Something put.
You're thinking of deconstruct BREP, and not quite yet. But so the other method of breaking this down, besides a rectangular grid, which is always planar, is divide domain squared. Remember that one? It's totally okay if you didn't until right now, because I only told you about it like once. So divide domain squared, we're basically just going to take this beginning part and we're going to replace it with our new subdivision and hope that it's going to work and give us extrusions, but I already told you it won't. But we're going to see what it looks like anyway. So let's first reference the surface into Grasshopper. And I'm just going to work adjacent to my definition here until I'm ready to connect it and apply this to that. Yeah, so right-click that, set one surface, and we're going to put it here. And if you care very much about how it looks, feel free to turn that default layer off, like that. Okay, so with the surface, right, we are using divide domain squared. And divide domain squared, I mentioned, is kind of like the holy trinity of like three particular components that are kind of named funny. And, you know, you just need to get used to what they're called, okay? And you're always going to see them in this configuration, at least for the foreseeable future. It's under math and domain, because remember, we're working within this is a good way to remember this. When you're using domains, it's because you're working within a particular boundary domain. That's where that comes from. So our domain for this operation is that surface. And we're going to divide it, right? So divide domain squared. All right, so this one is going to ask for the base domain. That's our surface. And then it's going to ask you for that U and V subdivision count. Remember, U's And u-axes and v-axes are the same thing as x and y, but they happen in a basically a warped dimension, in a way. All right, so surface is our base, and then we're going to create sliders here for the subdivisions, and we can just say, I think I only use 0 to 10 on that, right? Yeah, 0 to 10. Actually, what we're going to do is just use the same sliders. Let me put that out of the way. So the EX and EY, they're the same thing as the U and the V. So we can just plug in X to U and Y to V, and nothing will happen. Okay? That's because, remember, it's a holy trinity. Trinity is 3. There's a third one that we need in this configuration, and that was the really funny name one. Under surface and utility, it's this one right here called isotrim. Ringing any bells? Yeah, I see a couple of nods. It should ring a bell because I lectured you all on the fact that it's actually called subsurf when you drop it in. So, yeah. You just need to, it's one of those things like, I don't know, write it on an index card 10 times before you go to bed for the next 20 days or something like that, and you'll remember it. Yeah.
The divide component, where is that found in the Grasshopper?
Good call. That is under math domain. Thank you, everyone. You're getting it. And this is under surface analysis. Spelled that wrong. Analysis.
And it's just divide domain?
Yeah, divide domain squared. Yeah, that's the difference here. And actually, a funny little anecdote here on the side. I got a YouTube comment on my YouTube channel that somebody said there's an app that will do this for me automatically. So I'm gonna try and download that for you guys so I don't have to waste time typing. YouTube's a cool thing, huh? Anyway, so what we're gonna do here is we're gonna connect the surface input, right? So that gives it a base surface to divide. That's this. And then we're going to subdivide that surface. That's this guy right here. That's our domain subdivision. We'll plug that in, and this is what we're going to get. Okay, so the relationship between our curved subdivision and our 2D subdivision is that they have the same number of subdivisions, right? Now, it's a good idea to save right now.
I'm scared.
Yeah, because we might crash it. But I'm going to say, because I told you it's not going to work. So what we have is a set of surfaces, right? These are your 56 subdivided surfaces. We also have in our other definition, coincidentally, 56 subdivided surfaces.
So it's too much?
Well, so these surfaces right here they're just surfaces. Because of the fact that they're just surfaces, it really doesn't mean that they have to be in that orientation. So I can take these surfaces and replace it just kind of like this is a funnel to the entire rest of the definition. Without this, nothing happens. Everything exists beyond that. So if I can just take these 56 surfaces, I'm talking in theory right now. Theoretically, I could take these 56 surfaces and reapply it and just reconnect it there, override that connection, and this should just pop onto there and be in 3 dimensions, right? Yeah? Well, yeah, let's try it. But make sure you save first. And then you plug that in, and that's what it does.
Wait, what?
Sorry.
Just go up. Stacked up.
Yeah.
It's not going sideways? Going up and down?
It looks like Mondrian threw up, right? Well, what do you think is happening? What can we deduce from this mistake?
It's still going through the Z.
What's that?
It's still going up through the Z.
Uh-huh.
Like the Z?
Yeah, it's still going up through the z-axis, right? Because we extruded them in this direction. So what we're going to do today is reorient this so that we can get them all to extrude outward. That's our challenge.
Can you just flip the warp surface the other way so it goes up instead of changing the vector z?
Yeah, but then they're still going to go straight up, not straight up referential to their angle on the surface. Yeah. All right. Any other questions? All right, I'm going to stop this video and then we'll move on.